boundary of V must be regular. What it means regular? That in every point you have a tangent plane, okay, and you have a tangent, a normal vector to the surface. So also the boundary has to be regular. Of course, as you are calculating an integral, and this is crucial for what we will do in the next, in the applications for this, you can have a boundary like that, with the normal, which is jumping in some edges, at some edges. If you imagine a cube, okay, like that, you have here that the normal on this part of the surface and the normal on this other part of the surface are different, because this face has this normal, okay, here, and this face has this normal. So you have some curves on the boundary of your volume, which we call edges, where you have a jump of the normal, okay? So in a sense, the boundary of V has faces and edges. Faces and edges. Faces are regular surfaces where the normal is defined. And edges are curves, and we assume that they are regular, where the tangent vector is defined. Okay. If you have curves having area 0, there is no difficulty in defining this integral, this flux, through the surface. Okay? We will need to study the geometry of the boundary of a volume in greater detail in subsequently. So it is very important to have in mind that what we are doing is applicable even if you have this kind of boundaries with jumping normals on curves. Okay. Okay, so let us have now our volume V, and you have the side minus and the side plus. Why? Because you have introduced a plane pi, and this plane is cutting the volume in two parts. So V is equal V plus union V minus. And when you have, when you go back to the normals, which I'm drawing green, of V plus, you find that the outer pointing normals on the boundary of V plus in common with the boundary of V minus. So dV plus intersected dV minus, which is this region here, this surface here. Okay, on this surface, you have that n plus is equal to minus n minus. And this will be essential in what we need to understand now. So let us consider in this volume, which has been split in two, the vector field W. So these are normals. And now inside the volume, we introduce W. Okay, this is N minus, and this is N plus. Okay, so it is really evident that integral over the boundary of V of W dot N, okay, is the flux on the whole, let us make it blue, on this surface, okay, of the field W. Now, how it relates to the flux on V minus and on V plus. So even if I cannot draw exactly the same stuff, this is V minus, and we can write integral over the boundary of V minus of W dot N. Of course, you have a part of this integral which is on the boundary of V, and another part of this integral is, so this boundary of V minus intersection boundary of V plus. Okay, so you can split this integral. Let us erase for the moment the W, the equaling. You can split this integral as the integral over dV minus intersection boundary of V, and this is, let us do this with bolts, okay? Of W dot N plus integral over dV minus intersection dV plus of W dot N. Okay. Then you can write integral over dV plus of W dot N. I try to draw this here just in a schematic way for letting you have this clearly in your mind. Okay, this way. So you have, this is dV minus intersection dV plus, okay? And this is the part dV plus intersection dV. And similarly, you get that this becomes integral over dV plus intersection dV of W dot N plus integral dV plus intersection dV minus of W dot N. Okay, so we have that this addend becomes that, okay, and this addend becomes is equal to that, simply by decomposing the boundary and using additivity of surface integral. When you make the sum of these two integrals, what you get? You get that dV minus intersection dV union dV plus intersection boundary of V, so this becomes the whole boundary of V, while the normal, outer normal N on this integral, so here I should better write N plus to make the difference, and here I should write, and I will, N minus, okay. On this intersection, N plus is equal to minus N minus. So these two addends cancel. Okay, so we have this equality. So what we discover, which is very important, the flux through V minus plus the flux through the boundary of V minus plus the flux through the boundary of V plus are additive. So maybe we can call them phi minus plus phi plus equal phi. While phi minus is the flux through the boundary of V minus, and phi plus is the flux through the boundary of V plus. And this is an important indication, because think about it. If I have integral of W dot n on the boundary of V equal integral of something applied to W in the volume V. So this is an area, so a surface integral, and this is a volume integral. Then this property must be verified. Because if you have that integral on the boundary of V minus of W dot n is equal to the integral on V minus of something applied to, and the boundary of V plus W dot n is equal to integral of V plus of something applied to W. Clearly, these are two volume integrals and they are additive. So this is equal, the sum of these two is equal to the integral over V of something applied to W. And so this property must be verified also for the fluxes. So this property of fluxes is strongly suggesting us that there are some chances that we manage to find this strange operator. Okay. Okay. Now let us see the nice drawings in Wikipedia. This is what I said you up to now. Okay. So, okay, they wrote a different notation, but this is exactly what I said. Now, what they discover is that this flux phi 3.1 is minus phi 3.2. So it is useful if you reread this another time for understanding what I said you up to now. But you know, this picture is very nice. However, I want to underline that, you know, this picture may be misleading in a sense, because the surface is regular, while, as I told you, this theorem clearly applies even if the surface is piecewise regular. So if you have jumps of normals concentrated on curves. By the way, when you cut this volume in this way, you have an edge here. You see? And you apply the definition of flux through this region, even if you have a jump of the normal there. Why? Because if you change the value of a function integrated on a surface, on a curve, so changing the value of an integrand, a surface integrand, on a curve is not changing the integral value, because the area of a curve is 0. Okay, so the reasonings which we are considering presenting are valid also in the case of piecewise regular surfaces. unavoidable if you think about this cut, which is made there, and it is shown in this picture. Okay. Now, and this is very important for what you will do numerically. In every numerical application, you are exploiting this property. You take your volume, and the reason for which I want to show you this Wikipedia entry is that you understand that I cannot draw this by hand, okay? So if you split the volume in the unit of many different pieces, you can repeatedly apply the reasoning which we did for 2 surfaces. Of course, you will have troubles. Why? Because take this volume. It has one face here, one face. Okay, here it is better. You have this face, the bottom face, this other face, plus the external face, which is this one. So you will have cancelling of this surface integral when you add with this on the left. The surface integral of this face will be cancelled with the integral with this other region. The integral on this face will cancel with the surface integral relative to this other surface. But at the end, when you compose all these fluxes, you get always only the flux through the whole region. So I think this is very, very geometrically, this explains what is happening in a very clear way. And you always have that when you have a partition of the starting volume into sub-volumes, the flux calculated for the whole volume is always the sum of the fluxes for each element of the partition. I remind you what is a partition, which is also very important for finite elements. If you have a volume V and you have a family of VI sub-volumes of V, VI is a partition if VI intersection Vj is empty when I is different from J, and when the union of VI's is V.
Professor.
This is a, yes?
We cannot see what you are right.
You are right. Sorry, tell me this, because playing with 2 things, we should invent the eye control. When I see the tablet, the screen should change. Okay. We must work on this. So this is the definition of partition. I repeat it. When you have a volume, you have a family of subsets of the volume, Vi, and the union of these subsets is V, and the intersection of 2 different elements of the partition is empty. Okay? So whenever you have a partition of this volume, you can apply this formula. Okay, it is rather astonishing, you will see now, how this concept can be one of the most fundamental concepts of finite element theory. Because now, the partition of this can be done with tetraedra. I mean, with every kind of finite element partition you have in mind. But for simplicity, let us think about cubes. Cubes with, therefore, faces orthogonal one to the other, and edges which are orthogonal to the adjacent faces. So we will exploit this geometry soon. Okay, of course, you have troubles with the boundaries. Okay, but you are discretizing the boundary. So the idea, I will not go into too many details, but I must tell you this. And this is actually finite element theory. When you split this volume as union of cubes, of course, here you will have this part which is not included in your reasoning. So if you zoom in here, you have this region, and then you have, you know, this cube here, then you have this cube here. So you are approximating the boundary with a piecewise flat surface. Okay. However, this volume here can be made as small as possible. So, and this is the reason for which what I'm showing you is an informal derivation of Gauss theorem. What happens at the boundaries? Approximating with cubes the boundary, the volume, and with faces of cubes the boundary of the volume may be critical. However, we can prove that making the volume smaller and smaller, okay, the error in estimating this surface integral, replacing it with the boundaries of the partitioning volumes, becomes smaller and smaller. Actually, surface integrals are defined in this way. You know, when you have a surface, now I try to switch to my drawing, even if it is horrible. What you do, you always approximate this surface with small squares. So you transform this surface into a union of small squares, which are all tangent to the surface in the central point, and integral of a function psi on the surface is always sum over I from I1 to n of integral on the Ci psi, where Ci is this small approximating square. I mean, union, one of the squares needed for approximating the surface. Okay, so we cannot do a theory, a class on measure theory. The mathematicians, mathematicians are very strange. They called measure theory. What is that? The theory of generalized theory of integration, because they are measuring volume, surfaces, and length. So a beginner may believe that we are talking about how to make measurements in experimental physics. Okay. So the subject, we cannot delve into many details for this, but I think that the idea is well represented by this picture and by this equality. So the integral over the whole volume SV, the whole surface boundary of the volume V of phi dot n is the summation over every cube in this partition of the flux through the cube. This is not a strict equality, because if you want only cubes, then this integral is equal to that plus something which is small. It is smaller than epsilon times a coefficient when the side of this volume tends to 0 with epsilon. Okay. Now you can do this subsequent trick, which is for the moment only an algebraic trick. You can multiply and divide the flux here with the volume of the region which you are considering for calculating each of these fluxes. So in the case of our cube, you have the cube. You have the volume of the cube. So if the side is epsilon, so the volume of the cube is epsilon cube, and you divide times epsilon cube the flux through the surface. And the flux through the surface in general is a quantity which goes with epsilon square. Okay. So this is an important trick. So you divide the flux of our field, is calling it F. I called it W, no problem. You divide this flux times the volume of the small cube, so that you can write, okay, now they wrote limit. This is a very intuitive procedure, so that when, of course, there is an ambiguity here. Either these VIs are all cubes, and then this equality is not true, or you consider some of these VIs not being a cube on the boundary, but a side is faces of a cube and the other side is curved following the lateral surface of the volume. Okay, then, and this equality is true. Then you calculate this limit when the volume tends to 0. Okay, and then in Wikipedia they jump, because I don't know why one should see that this is producing the divergence of F. Okay, so now we will try to understand better why this last equality holds in general. And I have seen this picture in many places. I'm sure that many of you could see this picture in many places. However, I don't know why I could not find it. So even if it is not very, very nice, I am reproducing it here with a drawing. So you have, let's call it W. You have the vector field W function of X. Okay. Then you consider a cube having the faces normal to EX. So here we have the system EX, EY, EZ. For our reasonings, they must be orthonormal faces, so that N is equal to EX, and EX, EY, EZ are one orthogonal to the other. Okay, so you can consider the flux of W through this face here and that face there. Of course, we will repeat this for every pair of our faces. So what you have, this flux is, as this volume is very small, this is the area of the phase times W calculated in X plus dx here, dot EX, so that you need to know this angle there, plus W of X dot minus EX, because the other pointing normal is on the other side. Okay. So you can, the area is the same because of the geometry and the fact that we have everything orthogonal. Okay. So if we call Wx the X component of W, this is equal area times Wx calculated in X plus dx minus Wx of X. Now, this is the same variable than here and than there, because we must consider the variable, the coordinate along a line, and this Ex is the unit vector pointing in the direction, positive direction of this axis. Okay? So you can use Taylor expansion for estimating this increment here, so that you get Wx plus dWx over dx. This is the reason for which we will have the same variable for direction for projection and for calculating derivatives, times dx minus Vx calculated in X. So this simplifies with that. Okay. And at the end of the story, we have that the flux through these two faces of our cube is the volume of the cube times this partial derivative. Okay. Now, repeating this argument on, let's call this is E zeta, on the faces whose normal are E zeta or minus E zeta, and repeating this argument on the faces, this is minus EI y, and so on the other four faces taken pairwise, one in front of the other, you clearly understand that at the end, the flux through our cube is equal to the volume of the cube multiplied dWx over dx plus dWy over dy plus dW zeta over d zeta. And now you understand why Gauss defined the divergence in this way. Not only you understand why I am stressing all the time that the system of coordinates which we are using must be globally always the same. So you must have a unique basis for representing vectors everywhere in your field, and why this coordinate system must be orthonormal, because otherwise this reasoning with the cube must be modified somehow, and we cannot do anything else. We cannot proceed in our reasoning. Okay. Now let's go back to our last lecture. Okay, let me find it. This was on Monday. On Monday, we systematically applied the divergence theorem, which I've shown you now, but in a certain moment, we did arrive, let me find it. We did arrive to an integral which is 1. So I will copy this integral. Okay, this one. If you remember, we made some calculations, and we will repeat this with greater details another time, but no, if you remember, I cut this. Let me try to cut this if I manage. Okay, so I can go to this presentation here, and I can try to copy it here if I manage. Okay. There is not a lot of space, but okay. Where should I place it? This was not a very good idea. Okay. So I have on the boundary of a surface of a volume. So this is a surface integral. A quantity here. So let's call this quantity I have only the index I and B, so we can call this in a short way S I B. Okay, in our reasoning for the moment, this is not important. Okay, so maybe SBI, I can write it closer. Okay, then I can copy PCB. This is the projector in the plane of the boundary of C star. And then I have d over dxc of delta ki. Okay. So I have a surface, and here I'm drawing a part of this surface. Okay. And I have a differential operator applied to delta ki and a tensor with which this is saturated. So I want to apply integration by parts because I have an integral on the surface here, on this surface. Okay. And probably this is something not needed. Okay, I have an integral on a surface, and I would like to jump to place this partial derivative. Remark that these are only derivatives tangent to the plane of the surface. So in a sense, this is a parallel gradient of our field delta K. So the idea is, can I generalize divergence theorem, which I've proven up to now, to the case of surfaces? This is the technical difficulty which stopped Piola. Piola did not develop this part of his reasonings because differential geometry had not been yet developed his times. However, I must tell you, this is a remarkable feature. Piola was the maestro of Brioschi. Brioschi was the maestro of Beltrami. Beltrami was the maestro of Ricci, and Ricci was the maestro of Levi-Civita. So actually, you should understand this. Our life is not long enough. You are young, you believe that you are eternal, but when you arrive at my age, you start understanding that your time is ending. The job is so long that it is impossible that a single person, even if he's very clever and he will get Nobel Prize, it is impossible that a single person can end a scientific project he has in his mind. Piola died with an aneurysm. We know this because he wanted to have autopsy. He asked his colleagues, professors of anatomy in Pavia, to understand why he was dead. Okay, he died because of an aneurysm, being 56 years old, and he could not understand how to deal with this term, which I am now discussing with you. He understood that after the first integration by part, he had this term to handle, but he did not develop the reasonings, which I'm showing. I will be showing you in the next part of my lectures to proceed in the calculation. But he called on his bed of death Brioschi and told him, please publish this manuscript, teach these ideas to somebody, because this calculation has to be completed. We must, as human beings, understand how continua are exerting boundary conditions. You may believe that Piola was stupid, was crazy. If one among you understands that he was not crazy and that humankind is proceeding because of Piola's behavior, then you are the right person for doing a PhD with our group. Okay. So this process continued until Levi-Civita understood how to do this integration by parts. However, Levi-Civita did not attack the problem to be solved by Piola, and another French scientist called Paul Germain who, by the way, was secrétaire perpétuel de l'Académie des Sciences. He had a very relevant position in French Academy, applied Levi-Civita results to proceed in the calculations by Piola. And he did this in 1972. So Piola died in 1850, and we needed to wait 122 years before the scientific project of Piola could be completed. So what you must understand is that these things needs the interaction between teacher and pupil, and we need a school, because unfortunately our life is not long enough for completing this kind of scientific projects. Okay, now we have rested 5 minutes. Let's proceed. We will not end this argument today, but let us proceed a little bit. So now what we have? We have a tangent vector field to a surface. To remember in every moment of our reasoning that this is a tangent vector field, I write the components of this in the orthonormal basis, in the external orthonormal basis, which is always present in our reasonings. And even if my drawings are becoming chaotic, I repeat it here, okay? And I introduce again the projector operator, which takes the components of W and projects them on the tangent plane of the surface. Okay. In every location of this surface, we have a normal, which we call N. Okay. And W parallel here is a field of arrows, which is always orthogonal to N. Okay, so this is what we are building now. And we must consider the fact that we want to apply our results to a cube. Now, cubes have edges. So we have curves where the normal outer pointing normal is jumping. Okay, so we have some curves gamma, which are on the boundary of the surface N. What is the boundary of the surface? It's the set of curves where the surface ends. So this is the boundary of the surface which we have in mind, okay? And we have one curve constituting a part of this boundary. We allow the tangent vector to this curve here to jump, because here we have the tangent vector of this other curve here, which is not the same as the other one. So the tangent vectors of this boundary of the surface, which are curves, can jump in a finite set of, let's call them corners or wedges. In every curve constituting the boundary of the surface, we have the normal vector to the surface, the tangent vector to the curve, and the outer pointing normal tangent vector. So you could believe we are crazy. Nu, as usually is called this vector, is orthogonal to gamma. So it is orthogonal. It is also to N, the normal of the surface. So T is parallel to gamma, and nu dot T is 0. So nu dot T is 0 because this is orthogonal. And nu is also orthogonal with respect to N. Okay, so even if this drawing is not very good, I think you have understood the geometrical situation. Now we want to invent an integration by parts on the surface when parallel vectors W are involved. Okay, now which is the trick? Now, don't ask me why I know this. For sure, I did not invent this reasoning. I have read it somewhere, but I spent 3 days looking in my books and I could not find it. So at the end, in order to be sure that I was reconstructing this reasoning in the right way, I asked the poor Erden to spend some time with me in order to have a check. And I think that I did a good reproduction of the standard argument in this subject. Okay, now, which is the trick? which we have in mind. We take gamma and we build a small volume having basis gamma, moving along epsilon, along the normal n. So I have called small n the normal to gamma. I move, look here, epsilon, the point which is on the surface n. I move this point along the normal n and I place it at a distance epsilon. In this way, I am building the surface M epsilon n. Let's call it in this way. So I am translating along the normal every point of the surface M. Okay? And I am considering also every M H n where H belongs to 0 epsilon. So I consider every H translated surface where H is 0 and every number between 0 and epsilon, epsilon included. So what I'm building, a small slice, if you like, whose basis is the surface M. By the way, this argument you will find also in shell theory. So I think that it is very important that you understand the differential geometry, the essential of differential geometry I'm telling you now, because this is not only useful for edge forces in second gradient continua, but this is also very important in shell theory. Okay, and now I have a vector field W parallel. Okay, it is a vector field defined on the surface only. Now, the idea is that I extend this W parallel along this small having direction n and thickness epsilon in the most trivial way. It is constant. So in every point I define always, okay, the drawing here is terrible, so I will not try to continue this. So imagine I have W parallel, and in every point of this segment, I translate W parallel, and so I am extending vector field parallel to M in the whole region V epsilon, which I'm defining as the union of these H translated surfaces, okay? And along each of these segments, W parallel is constant. Okay, as Erden remarked, I must say at this moment, so I thank Erden for his patience, grad parallel W dot n, so the normal derivative of W parallel along n is 0. This is clear because we constructed W parallel in such a way that it is constant along the thickness. Okay. Now, okay, here I'm repeating. So let's repeat once more my definitions. MHN is the translation of H, at a distance H. Along n of every point of the surface M. So in formulas, x belonging to M is transformed into x plus HN. So this is a very simple formula. Okay, and you understand what we are doing. And V epsilon is union of all these surfaces. And W parallel is prolonged in the whole V epsilon by giving a constant values on the segments which are built x plus HN, where H belongs to 0 epsilon. Okay, so W is now defined in V epsilon, in the whole V epsilon. Okay, now this vector field, for this vector field, you can define the remark that the parallel is with W. There is no grad parallel. Grad parallel we will define later. Okay, so the gradient of W parallel is, as we have defined in a standard way, D over dxa WB parallel. Okay, and the divergence of W parallel is D over dxa W parallel A. Now, W parallel defined in M has been extended in V epsilon. Why we did this? This is a typical reasoning made by clever mathematicians. I have a theorem which solves for me a simpler problem. I use this theorem applied for a simpler problem as a lever for solving a more complex problem. So I want to generalize divergence theorem to surfaces for tangent vector fields. Okay, I have already proven a three-dimensional divergence theorem. What I do? I prolong W in a volume V epsilon, and I am allowed to write this formula. This formula is applicable when N, remark, is the normal of N is orthogonal to boundary of V epsilon. Okay, now what we must now understand how this normal is built. So at the bottom surface, the outer pointing normal is minus N. At the top is N, small n. So capital N is the outward pointing normal to the boundary of V epsilon, while small n is orthogonal to M, to the starting surface. Okay? And we have that the outer pointing normal N on this lateral wall here, on this lateral wall there, okay, is easily recognized to be nu, which we have defined before. Because this nu has to be orthogonal to N, and this nu has to be orthogonal to the tangent vector T, to the curves, by construction of this slice in the space. Okay, but let's do it slowly. So the boundary of V epsilon is made by M epsilon n, the surface at translated epsilon. M, the surface from which we started, and the union of all these segments. So I have X on the boundary of M, and I built all these segments. Okay, we will call this lateral wall. Okay, very well. Now let us make flux of WA and WA parallel NA, this flux there. We split the boundary of the epsilon into its faces. We have the top face is M epsilon n. The bottom face is M. The lateral wall is LW epsilon. It is better if we call it LW epsilon. Okay? Trivially, this inner product is 0 because W parallel is parallel. So it is orthogonal to n, small n. Also, this quantity is 0. So the total flux reduces to the flux on the lateral walls. So you understand slowly the idea of the reasoning. Okay, I think that we will stop here. So we conclude this argument and we will complete next Monday our reasonings. Okay. So let us focus on this integral here. So the flux of W parallel is the flux on the lateral wall. And then when epsilon tends to 0, this flux is clearly the integral on the basis times epsilon, because the field which we are integrating is constant along this thickness. Okay? And this is where nu is orthogonal to the tangent vector to the curve gamma, and nu is orthogonal to n. So this is exactly the flux of W parallel through the curve gamma. Okay, so I think that we stop here because next Monday we will need to complete this reasoning by calculating the volume integral, which becomes a surface integral, and we will see which is the new divergence operator to be considered, which will be the surface divergence operator. Okay, so let's stop here. Erden, do you think I was slow enough?